Okay, hello everybody. We should start. This is Math 1151, and today we're going to talk about limits and infinite limits. I got an email from somebody asking me if we could calculate limits numerically, because what you can do is if you have a difficult limit, you could just type in, if you want to go have a limit that goes to 0, say you're trying to do this problem. Say you're trying to do the limit as x goes to 4 of 4 minus x all over x cubed minus 7x squared plus 12x. You could take your calculator out and you could type in 3.9, right? And plug it into that. And then 3.99 and 3.999, right? And that would give you a number. That's a very good way to estimate limits. It's a very good way to gain some intuition. However, on the exam, we are going to make you do it algebraically. And if you try to do it with your calculator, we're not going to give you many, if any, points. Okay, does that make sense? I know it's terrible, but I'm just telling you the facts. All right? Does that make sense to anybody? You're like, no, that does not make sense to me, but that insane attitude that you have. And you might say, well, why do we insist? And one reason is, remember, we did a limit in class where you typed in 0.01, 001, 0001, and it gave you the wrong answer, right? Do you remember this? It was this limit here, f of x equals sine of pi over x. Remember, if you type in as, and we want the limit as x goes to 0 of f of x. And remember, if you plug in, by the way, what is the answer? What is this limit equal to? What happens here? It oscillates wildly, so the limit does not exist. Okay, I'll write that down in red so that we know that this limit does not exist. Okay, but if you type in 0.1, 0.01, 0.001, you're going to see a pattern here that's not real. Does that make sense? The videos should be up soon. We've been editing them. We've been having some success. Okay, and by editing, I mean the camera makes 3 videos, and we have to glue them together and chop off it's not much, but we'll see. I'll send you guys all a mass email when we get it. All right. So here, let's start off with an easy problem. Really easy problem. You guys ready? Limit as x goes to 10 of 42 times pi. What's that equal to? (42 times pi). There's nothing changing here. It's a constant, okay? So that one's easy. So let's hope that we all get this one on the exam because it's easy. Okay, I doubt it. I expect you to get something more like this one here. Okay, how do we do this one? What do we do here? Factor the bottom. And how, first of all, we should note, what's the very first thing you should try? Factoring the bottom is great, but what's the very first thing you should try to do? Plug it in. And if you do, you get 0 in the denominator, and you get 0 in the numerator. And so that's a problem. Okay? So factor the denominator. And so this is equal to the limit as x goes to 4 of 4 minus x over. And how are you going to factor the bottom? Factor out an x. Sounds like a great plan. X squared minus 7x plus 12. And now what do we do? What do we do now? We continue factoring, right? And this is a quadratic down here, and we're good at factoring quadratics. So this is going to be x times, let's see, x minus 3 times x minus 4. So now we have this. What do we do now? Yeah, that's a really good thing to do. Okay, so he says, take out a negative sign, limit as x goes to 4 of minus 1 times x minus 4 all over x, x minus 3, x minus 4. Now we can cancel because x is not equal to 4. X is just near 4. Canceling. All right, and now this is equal to the limit as x goes to 4 of minus 1 over x times x minus 3. And we can just plug in, and what do we get here? We get minus 1/4. We win, right? Oh, and what's a good thing to do when you get your final answer? Put it in a box. That's always a good thing to do. Then the grader's like, where's the answer? You know, and then you put it in a box, and I don't know. Okay, so that's not so bad. Any questions on those two problems? All right. Here is, we're going to do 3 more basic limits before we keep on going. I just want to do as many of these as possible. How about the limit as x goes to 3 of 1 over x minus 3 times 1 over square root of x plus 1 minus 1/2. We try to plug in first, right? Yeah, we get 0 here. And what happens over here? It's also 0, right? And so this is like the numerator in this case. Now, I looked at this problem. I don't know. This one looks a little different to me than the previous ones, okay? And so maybe we should try something a little different. Although, right. The problem is that we had the square root of x plus 1 here. And I didn't really like it. So I replaced it. Square root of x plus 1 is equal to y. And now this tells us that y squared minus 1 is equal to x. Is that true? Oh yeah, totally true. Right? I just solved. Okay, so we plug in. Haha. So if the limit as x, this is the limit as x goes to 3, this is going to become the limit as y goes to what? What should y go to if x is supposed to go to 3? Plug in 3 here. 2. Y goes to 2. It's the limit as y goes to 2 of 1 over. Now x is equal to y squared minus 1, right? So it's going to be y squared minus 1 minus 3 all times 1 over y minus 1/2. Now what I want to do here is, I don't like those fractions. I mean, look, fractions make our life harder. Why did I, but by the way, I'll give you one hint as to why. You might say, well, how did he know to do this? Right? How did he decide to do this? And the answer is, I fought with this problem for a while. It wasn't like I saw it and I said, aha, do this. I tried a couple different things first, okay? And one of the issues that came up is that dealing with the square root and the x here, I didn't like dealing with both of them. I wanted it to all be individual variables. OK, so what comes next? Well, next I want to get rid of the fractions. So I should add these together. So then this is going to be the limit as y goes to 2 of 1 over, what's that, y squared minus 4 times, and then I have to put these over a common denominator. So that's going to be something over 2y, am I right? And what's the numerator going to be? Oh, 2 minus y. Is that correct? I'm getting some nods. Some. How am I feeling right now? Am I feeling, are we close to the end or not? We are close to the end. Okay, we really are. Because, look, limit as y goes to 2. Well, this thing's going to be 0, right? This thing's 0. How does this thing factor? It's the difference of two squares. It's equal to the limit as y goes to 2 of 1 over x minus 2 times x, sorry, y minus 2, y plus 2, all times, I'm going to do it fast, y minus 2, all over 2y. So what can I do now? I can cancel. And at this point, I'm done at this point, because this is the limit as y goes to 2 of minus 1 all over y plus 2 times 2y. And can I plug in 2 here? Yeah, I can. So this is going to be 4 times 4. This is equal to minus 1 over 16. Yes? Yeah, because, so he said, why did the limit change from 3 to 2? It's because I substituted y equals square root of x plus 1, right? So that means y squared minus 1 equals x, right? So now plug in 3 here. So if I'm taking x to 3, this whole expression goes to the number 2. And that's equal to y. So y is going to the number 2. Yes?
Can you explain how you went to 1 over y minus 1 half?
1 over y minus 1 half. Right here?
Yeah.
Excellent. Yeah, I can try. OK, so what I did here was I added, these are two fractions, and I added them together. So I put them over a common denominator. The common denominator is 2y. Here's the common denominator. And then I had to multiply this fraction by 2. So it's 2 minus the numerator of this fraction times y. Did I answer that question for you? Yeah, I can write it down. OK, so it's the limit as y goes to 2 of 1 over y squared minus 4. And then put it all over common denominator. So the common denominator is 2y minus 2y, right? There's the common denominator. And so I had to multiply this one by, that's 2 over 2y is 1 over y. And this one is y over 2y. Is that better? Can anybody see this down here? Can you guys back there see this? Now you're nodding your head, yes, that sounds good. Yeah. We don't. She asked, do we need to switch the limits back to x's? No. All right. I just looked through your book and looked through some, I have like 5 calculus books lying in my house and office. So I started looking through to try to find ones that look different, because I don't want you to be surprised as much as possible. How about this one? Limit as theta goes to pi over 4 of sine squared theta minus cosine squared theta, sine theta minus cosine theta. What's sine of pi over 4? Pi over 4 is 45 degrees. That's right. Root 2 over 2 or 1 over root 2. It's the same number. Okay? Sine of pi over 4 equals square root of 2 over 2, which is equal to 1 over root 2. Yeah? That minus 1 over 4 was for another problem entirely. Yeah, so it was, you know what, it was very confusingly written. I'm sorry. I'm trying to, I should put more little, this is, here, boom. Yeah, I forgot my box, okay? You guys can tell me to put the box in and I'll box it in. All right, so sine of pi over 4 is square root, what's cosine of pi over 4? Same thing. So what do we have in the numerator here? 0. What do we have in the denominator? Okay, what do we do? This is a hard problem. Oh, you gotta, yeah. Factor the top as the difference of two squares. That's exactly right. Okay, pi over 4, and then the numerator becomes sine theta minus cosine theta all times sine theta plus cosine theta all over sine theta minus cosine theta. Cancel, cancel, right? And we get the limit as theta goes to pi over 4 of, oops, no more fraction. Sine theta plus cosine theta. And that's equal to 2 over the square root of 2, which is equal to the square root of 2. There we go. What was the trick? Remind me what the trick was here. Difference of squares. We love to disguise difference of squares. What's another way we could disguise the difference of two squares? Yeah? Make one of them a 1. That's exactly right. Something else we could do is we could hide one of them as an exponential function, right? We could say something like this. I'm making this up, so I'll probably screw it up. But here we go. It's going to be like e to the 2x minus e to the, 4x here. This is the difference of two squares, isn't it? Yeah, I'm going to have trouble making that equal to 0. Oh, how about we do e to the, what's here? E to the 2x minus 1 all over e to the x minus 1, the limit as x goes to 0. There we go. What's e to the 0? 1. So e to the 2 times 0 is 1, right? So what's the numerator? 0, what's the denominator? But this is the difference of two squares, isn't it? This is e to the x plus 1 times e to the x minus 1. Don't forget your limit, Bart. You're disrespecting the equal signs. As x goes to 0, all right, e to the x minus 1. I can cancel these out. And I get this as limit as x goes to 0, e to the x plus 1, which is equal to 2. Does that make any sense? Maybe? If it doesn't, can you ask me a question? All right. Last basic limit before we move on to section 2.4. Here it is. The limit as x goes to 0 from the right of the square root of 1 minus x plus 2 minus the square root of 1 over x. What do we do here? Can we plug in? Can we plug in 0? The first term goes to what as we plug in 0? It's undefined, right? But the second term is also undefined as we plug in, as we set this to 0. So what do we do? Yeah. This is x goes to 0 from the right. That's correct. That's exactly correct. You know what I might be tempted to do if I saw this? I'm taking a test. I see this on my test. I have a graphing calculator. What do? I graph it. That's right. And when I graph it, I find this. The graph looks like this. What's that tell us? Yeah? It looks like what? It looks like 1 over x. 1 over x actually, he says it looks like, actually 1 over x looks like this. E to the x looks like this. It looks like square root. It looks like square root, right? What's the limit equal to, though? What's it look like the limit's equal to? 0. It looks like the limit's equal to 0. Okay? Now, we might be tempted just to write 0 down on our paper, hoping for some points, okay? But probably that's not going to work. And by probably, I mean almost certainly, okay? And by almost certainly, I mean it's not going to work. So, what do we do? What do we do in this case? We should be fearless. There's one thing they're screaming out at us to do here. Even if we don't see, you got to proceed sometimes and not know how it's going to help you. What do you do? Yeah? We can set 1 over x equal to y. That's a good idea. And that's actually a really nice idea. Okay? He says set 1 over x equal to y. If I set 1 over x equal to y, what's the limit become? It goes to infinity then. And that kind of that's a good idea. It's a good idea. It kind of complicates. Yeah? We could try to factor. We can't factor. I don't know how to factor. It's too many square root signs. What do you do to get, yeah? We could square the whole thing. That's a great idea. Okay, when you square the whole thing, though, you might be tempted just to remove the root signs. Can you do that? No, you're going to have these cross terms, and they're going to really bugger you up, okay? Boy, this problem is hard. What's another thing you can do? When you see square, yeah? Yeah. It's that he says maybe I could write it as exponent to 1/2. It's a great idea, you know, but it's not going to help because it just changes the form not enough. That's a great idea, okay? These are all good ideas, yeah? Yeah, she says multiply by the same thing, but we have a addition sign, right? Addition sign. What's that thing called where you the conjugate. Okay. But if you're sitting in the audience and you hear this answer and you say, well, Bart says that sounds good, but you know what? I don't think we're allowed to multiply by just random numbers. Okay, she has the right idea. How do we multiply by random numbers if we want to? The top and bottom, we multiply by a fraction that equals 1, both which have the conjugate in here. So we're going to say this, limit as x goes to 0 from the right of the square root of 1 over x plus 2 minus the square root of 1 over x all times By the way, we just had a very accelerated conversation about ideas to try here. If you're doing this yourself, gosh, that might take you 30 minutes or more to try to sort all that out. How are you supposed to do that on an exam? What's the answer to that question? What? Write faster, right. You're supposed to write faster. You're supposed to be clear. Yeah, you have an answer? You're supposed to do, that's a good answer. You're supposed to do everything you can first, okay? Everything you can first. But the other thing is, you're supposed to have done it before, okay? I don't know about you, but I used to like to go into the exam and be like, I'm going to figure out these problems for the first time right now. That's exciting. No, okay? That's a terrible idea. What you should try to do is you should try to exhaust our source of questions, okay? And say, I'm just going to do all of them, and I will have seen every single problem here before somehow. That's what you should try to do, okay? And then when you don't see problems, you shouldn't get, when you're there and you're like, okay, I know, oh my God, I've never seen this problem before. Don't freak out. That's when you say, wow, this is exciting. Let's get going, you know? Yeah?
You say to exhaust the source of the complex problems or whatever. Where exactly is that source coming from? In the book or is it pretty? That's my problem usually. I always see everything in the book and then there's something that wasn't in the book on the test.
Yeah. So he says, he says, we use the book for problems, right? But what if, somebody says, well, they already did all those book problems. Now we need to put something really hard on the test, right? I'd recommend you can go to the library. Guess what? All calculus books are the same, okay? The numbers are different, but some of them have slightly harder problems. You go to the library, okay? You can go online. You can go to, remember Mooculus? Have you gone there? There's lots of problems to do there. Okay, if you don't like them, you can send me a personal email saying, Dear Bart, nice problems, not. And then I'll be confused because I'll read it as, Dear Bart, nice problems, not. Wait, I don't understand. Okay, well anyways, let's finish this problem. Okay, so here, oh my God, I can't remember what we're supposed to do. What are we supposed to do here? Multiply by the conjugate, that's right, okay? Never a bad idea. Well, maybe it is, but here. 1 over x plus 2 plus square root of 1 over x, square root of 1 over x plus 2 plus the square root of 1 over x. Okay, and then what happens? We get the limit as x goes to 0 here. What happens to these two things? What happens? It's like the difference of two squares, right? That's what we just did here. That's what we just did here. And now we're doing it here, but backwards. Okay? It's going to be this squared minus this squared. So it's the square root of, oh no, sorry, it's squared. Aren't you paying attention, Bart? Okay, so 1 over x plus 2 minus 1 over x. And how do I feel? I haven't even written the denominator down yet, but how do I feel at this point? I feel happy, right? Why? The 1 over x will cancel. I save to savor that later on. I wait, and then I have 1 over x plus 2 plus square root of 1 over x. Okay, and this is equal to the limit as x goes to 0 of 2 over the square, oh, from the right. Yep. 1 over x plus 2 plus square root of 1 over x. And you might say, well, I'm still stuck, right? What happens here? I say we're done. What happens here? The bottom here, the top is constant now, right? The top is constant. And the bottom, what way is 0 coming from? From the right. That means we're putting larger and larger, we're putting smaller and smaller positive numbers here. And 1 over a small positive number is a large positive number, right? So the denominator is going to go to infinity. And so this will be equal to 0 because the denominator, the numerator stays constant, and the denominator gets very, very large. I'll write that down. Gets huge. Yes, back there.
So once we have a constant on the top, then we're allowed to go ahead and say, well, you can see if those two things.
He says, once there's a constant on the top, are you allowed to just to plug in the 0 and say that this goes to be infinity? Yes, basically. The one exception to this, since we're coming from the right, that simplifies things. If we just said going to 0, you'd have to check it from the right and the left. Okay? I've been working on not saying okay so much. I watched my videos and I'm like, oh my God. Okay, so yeah. But there's hope for us all. All right. I think that, yeah. What'd you say? Does 1 equal 0? No! Thank you. Thank you. It looked like 1 equals 0. No. 1 never equals 0. Okay? You don't get what we're doing. You got up to here, right? Am I okay? Are you okay with that? Okay, she says, I'm not real sure what happened here. Here, I'm going to solve an easier problem, and it's going to make this one make sense, I think. Okay? Here it is. One over x, like this. Limit as x goes to 0 from the right. Okay, so x is going to 0 from the right. So what we're going to do is we're going to get out our calculators and plug in our favorite little numbers. Okay, and so this is like saying 1 over, what's 1 divided by 0.1? You can do this in your head, and if you can't, you're going to learn today. It's 10. This is equal to 1/10. What's 1? This is the limit as x goes to 0 from the right of 1 over, what's 1 over, I'll have to take this out. 0.01. What's 1 over 0.01? 100. So this is equal to 1 over 100, right? That's what's going on here. We're plugging in small numbers, and we're doing 1 over a small number. It makes a big number, all right? And that number gets as big as you want. 1 over 0.001, that's equal to 1 over 1,000. Since it's 1 over x, and x is going to 0, this number gets really, really large. So this whole fraction gets very, very small. And the reason we couldn't do that immediately It's because we were subtracting stuff, and we seem to get like 0 minus 0 or something, or infinity. It's confusing. Why do we have the plus in there? Does anybody know? From the left, the square root doesn't exist. That's the problem. We just have from the right because of the square root. What? It doesn't help that, it doesn't change the problem so much. That's the problem. He said, go ahead.
I wanted to give you the idea, since it's saying it's coming from the right, that the square root goes to the either more than likely.
Oh, that's a good point. Okay, so this guy says maybe this is a hint because the square roots, because it's coming from the right, the square roots will still be in your answer at the end of the day. Maybe. Okay. Just work through the algebra and you'll be better off. Okay, there's no shortcuts. All right, none that I know of anyways. Let's look at 2.4. .4 is about infinite limits. All right, so I'm going to give you an example of an infinite limit. Here it is. This is what I think is the prototype of all infinite limits. Limit as x goes to minus 1 of 1 over x plus 1 squared. If you get out your graphing calculator and you graph this, if you plot this, you're going to find this is. It looks like that. Where this point here. So as you go to -1, what happens to the y value? If you go to -1 from the left, what happens to the y value? It goes to infinity. And what's it? Here, you might say, what's that even mean, goes to infinity? It means that if I give you a big number, you can shove x's in that are closer and closer to 1 that are bigger than whatever big number I give you. So if I give you 1 billion, you could say, well, we just make it this close to -1, and then this is eventually above 1 billion. That's what you say. And what's the limit as we come from the right? It's also infinity. So what's the limit equal to? Infinity. And the reason is you say the numerator stays constant, and the denominator goes to 0, but it goes positively to 0 because it's squared. You should check the left-hand limits and the right-hand limits. You should say this. The limit as x goes to -1 from the right of 1 over x plus 1 squared. You say, well, the denominator is constant. It's constantly positive. And this thing goes to 0. And as it goes to 0, what is it? Is it positive or negative? It's always positive. We're going to 0 and we're always positive, so it's infinity. And the limit from the right is the same. From the left is the same deal. All right. Let's do a slightly harder problem.
So is it safe to assume that when the numerator stays constant and the denominator goes to positive infinity, it's always 0, and then when the numerator stays constant and the denominator goes to 0, it's
She says, is it safe to assume that when the numerator stays constant and the denominator gets huge, is it 0? Yes. Okay. And then she says, is it safe to assume that when the numerator stays constant and the denominator goes to 0, can you say it's infinity? You can say it's plus infinity, minus infinity, or does not exist. Okay, and so we're going to get to that right now. Okay, so it's one of those three. So here we go. The limit as x goes to 3 of 2 over x minus 3 cubed. If you plot this thing, it looks like this. Okay, and so what's the limit from the left? The limit from the left is negative infinity. And the way you would see that, so what is this? Does this limit, what happens with this limit? What's the answer? It doesn't exist. This limit doesn't exist, okay? But let's see, the limit as x goes to 3 from the left, it's 2 over x minus 3 squared, cubed, I mean. So this stays constant. And this thing goes to what number? 0. Goes to 0. And what is its sign as it goes to 0 from the left? Negative. Because the type of thing I'm plugging in here is like negative 3.5, right? Negative 3.5 minus, oh, sorry, it's like 2.9. 2.9 minus 3 is negative 1. Cube it, still negative, but is negative. Therefore, minus infinity is the answer here for 3 from the left. But the limit as x goes to 3 from the right of 2 over x minus 3 cubed, what do you notice about the numerator? Oh, I just said it. It's constant, right? And the denominator, let's see, if we're approaching 3 from the right, that's like saying 3.1, right? 3.1 minus 3 is 0.1. It's positive, 0.1 cubed. This goes to 0, but is positive. Does that make any sense? Okay. This one's coming from the left, and then you have to look inside the expression. You can't just look here. You got to look, you got to plug in some numbers, think about it, okay? It's not so simple that you can just say it's coming from the left, therefore it's, yeah. I would show something like this. It wouldn't hurt to draw the graph, okay? But what you really need is you need to say the numerator is constant, and the denominator goes to 0, but is negative as it goes to 0. I think so, yeah. Yeah. Who? Somebody else? Yeah. What do I mean when I say it goes to 0? Okay, so we're going to 3 from the left here, right? 3 minus 3 is 0. So this is saying, well, how you should imagine limits. This limit here, what we're imagining is you're like a point on the x-axis. And you're sliding along, and you're getting different y values here. And you're coming from the left. And so this is going, the denominator here is going to 0. That's what's happening. But did I answer your question? And yes. Plug in 2.9. He says that's not 0. But 2.9 is close to 3. And it's on the left of 3. Right? So I'm imagining a number line. I have 3, and here I have 2.9, and here I have 3.1. And so that's what I'm thinking about. Does that kind of clarify it a little bit? Yeah.
So does that limit not exist?
This limit does not exist. All right. Oh. She says, goes to 0. This should probably say the denominator, right? And she's saying, are you saying that if you plug in numbers to get closer to 3, but are still less than 3, the denominator is going to 0? Yes, that's what I'm saying. But it stays negative.
Okay, so when it goes to 0 on the denominator, but it's positive, that means it doesn't exist.
Yeah, but also the constant here is since it's not changing the sign, yeah. And so wait, this is equal to negative infinity, and this one's equal to infinity. Did I get that wrong? No, I did it right. What's up? Aha! He says once this thing, it says x goes to 3 negative. This means x goes to 3 from the left, from this side. This plus here means x goes to 3 from the right. That's what that means. All right. We're almost done. Almost done. How about this one? One more example and a definition, and I think we can stop. So here we go. Limit as x goes to 4 of x minus 5 over x minus 4 squared. Okay, so now you're taking the exam. You see this limit. It looks pretty innocent. What do we try to do first? Plug it in. Okay, so what happens when I plug 4 in? The denominator is 0. So you might say, aha, I want a factor. But what's the numerator? The numerator is 1. Negative 1, in fact. Right? Because the numerator is not 0, you're not going to be able to factor. Okay? The numerator goes to some number, and the denominator goes to 0. This thing's going to be positive infinity, negative infinity, or it's not going to exist. So, let's look at this from the left. The limit as x goes to 4 from the right is going to be, what happens to the numerator? This thing goes to, the numerator goes to what? Negative 1. The denominator goes to 0, and it is, let's see, we're coming from the right, so that's like 4.1 minus 4, which is, but squared, so it's always positive, right? And is positive. So what's that tell you that this is equal to? This goes to negative 1 over something positive. Goes to negative infinity, okay? So now, let's look at the limit from the left. The limit as x goes to 4 from the left. x minus 5, x minus 4 squared. What happens to the numerator? Numerator, what happens here? Goes to -1. The denominator goes to 0, and it's positive. So this is equal to negative infinity as well, so this is equal to negative infinity. Oh. And if you would plot this, by the way, the plot looks just like so. Like that. Where this is 4. We can end here for today. See you guys Friday.